Howdy y'alls. It is I, the Diabolic tutor, Diabolic vTutor once again. And today we're going to be going over factoring polynomials, specifically of the cubic type. So moving on from the quadratic to the cubic, and then hopefully sometime in the future, more random problems involving factoring a random mix of polynomials, including quadratics, cubics, and then other ones with more absurd exponents, but nothing beyond 5, I would say. Alright, so let's first talk about factoring something like a quadratic first, because ultimately what we're trying to do is we are trying to find the zeros of the function. And finding zeros for a function can serve us in multiple ways. Either you're trying to quote-unquote find the solution of the equation, you're trying to find the x-intercepts of the equation, you're trying to graph the equation, or you're just doing it for some arbitrary reason. But for the most part, the majority of what we're going to be doing in terms of finding the zeros is to either find the solutions of the equation, or we're just going to be using it for the purposes of graphing. So just between those two things, and just to talk about some of the vocabulary terms or the phrases or the vernaculars, there are some words that are, for all intents and purposes, practically synonymous. Okay, so you're going to be working with polynomials. You're going to be seeing the word solutions. Basically, you're just setting something equal to 0, and then you're solving for it, and that's referred to as solutions. That is also referred to as roots. And like I said, these are almost synonymous. Let me put that up on top just to qualify what I'm writing down. So almost synonymous. They're not the same thing, but for most of our purposes, they are of the same idea. So almost synonyms. We have solutions, we have roots, we have zeros. Is it zeros with an E or is it zeros with an S? I don't know. I guess it depends on what region of the world you're at, but we don't care as long as we understand what we're talking about. Spelling is inconsequential as long as we get our message across. So zeros, roots, solutions, and then factors. Again, these aren't equivalent, but they all share very similar ideas. So factors. Then there's like a few other ones as well. Oh, x-intercepts, you will see. X-intercepts. What else is there? Well, for the most part, that's the vast majority of the almost synonyms you will get. So when you learn about solutions, the roots are almost synonymous. Zeros are a type of solutions. Factors can be gotten from figuring out zeros. X-intercepts can be gotten from figuring out the zeros or the roots. As you see, it's all basically the same intertwined idea. But more on that a little bit later. So if you're given something like a quadratic, let's just take a quick review. We have x squared minus, what's my favorite number? It's 40 for making these type of problems. And then they are, the factors will be of different signs. And all I'm going to do is cook up the problem. So 20 times 2 is 40. So I'm going to subtract those two, thereby getting a 17. So this is our function. I'm going to name it h of x, because everybody always names it f. The cooler people name it h. So h of x is equal to x squared minus 70x minus 40. If you recall, you could use whatever algorithm you wish. It doesn't matter as long as you're comfortable, or you're following the directions of the problem. So factors of 40 that could possibly summate to be 17. We have 1 and 40. Nope. We have 2 and 20. Nope. We have 4 and 10. Nope. We have 5 and 8. I hope I didn't mess up the problem, did I? I said 20 and 2. Oh, okay. Yeah, I messed up the problem. That's okay. I am going to retroactively, so pretend you didn't see anything, right? So let's pretend I had instead written 18. I think that's what I had meant originally, so you didn't see that. All right. Thankfully, vTutors will skip straight to this problem. So we have factors of, we ask ourselves factors of 40 because we know that this thing times this thing has to give us 40 because of distributive property. And we also know that the x here and the x here that comprises x squared will have to multiply to that number and this number to summate to make the negative 18. So the only combination that could potentially lead us there is this 2 and 20. Alright, so cleaning up the work, we're going to get x with a 2 and then x with a 20. The question, how do we put the signs? Both signs are different, and then the larger of the two magnitudes, which is x times 20, must be negative. And since we want to produce a negative 40 for the constant, then this one has to be positive, because positive 2 times negative 20 gets us negative 40, and then the summation of this product with that product gives us negative 18x, which is consistent with the original problem. So that's just the mechanics of what we're doing. We're just trying to factorize the polynomial. This is what we get when we factorize it. And for prior problems, or last time, this is basically where we had left off, just factorizing the polynomial. And just to reiterate the vocabulary, this one is referred to as a factor of the polynomial. This is factor number 1. I'll call it 1 arbitrarily. This is factor number 2. And this is just familiar vocabulary, because if you have a number like 8, like 6, for example, not 8, I'll pick 6. If you have a factor like 6, if you have a number like 6, you can factorize it into something times something else, or something times something else. But we'll choose the prime factors. So prime factor 2 times prime factor 3 gives us 6. So this is factor number 1, and this is factor number 2. This is just for a constant, but the polynomial, we can think about it in terms of the same way. What times what can produce a polynomial? It's, in this situation, it's x plus 2 as factor number 1, analogous to this, times factor number 2, which is analogous to this, produces the polynomial function h of x, which is like these two. The product makes 6. The product makes h of x. So we're just breaking up our polynomial into factors, because we're going to ask ourselves, how can we produce 0? That's typically the ultimate question that you're going to be doing. Ultimately, how do we make this into 0? This is basically exploiting something called the zero product property, because as long as one of these factors is 0, if you multiply to a non-zero factor, then you produce 0. So if factor number 1, if we can somehow conceptualize how to make it 0, then this whole product of this factor times that factor will give us 0. And then of course we can think about the other way. If we have a way to make the second factor into 0, then it doesn't matter what the first one is, because if we have 0 times a definite value, we're going to get 0. So in this situation, there are 2 ways in which we can generate a 0. How do we do that? Well, how do we make the first factor into 0? If the first factor is negative 2, then let me colorize this real quick. If we make x equal to negative 2, if we plug in negative 2 into x, negative 2 plus 2 yields 0, and then 0 times anything definite is equal to 0. So that's why this is called a 0 of the function, because it literally produces 0 if you plug it into x. So that's going to be the solution, the 0 number 1. But remember how I told you that there's an almost synonymous phrases? Instead of calling it a 0, you can call it a root. Instead of calling it a root, you can call it a solution. It doesn't matter. Just get used to whatever convention your teacher or your book adopts, but it's just words. And words depends on your context. Okay, so again, we ask ourselves two questions. How do we make this factor into 0 if x is equal to -2, which is just relying on simple algebra. How do we make this factor into 0? It's if x is equal to +20. So again, these two are called zeros because if you plug them back in and multiply, you get 0. If you plug this in here, you're going to get 0 times 22, which still produces 0. So hence, these are called zeros. I think this is like the British spelling maybe, and then this is more North American spelling. I'll just spell it like this. So zeros without the e because it's less words, it's less letters for me to write. So zeros are right here. These are called factors. So when you look at this as x plus 2, that's referred to as a factor. When you set it and solve for 0, this is called a zero or roots or a solution because you produce 0. So in summary, we have a polynomial. You use whatever factoring algorithm that you've learned. You set it equal to 0, and then you solve by asking yourself, can I make each factor produce 0? And if you can, then those are your solutions. And that's what you're trying to do for these different scenarios. That's with a polynomial of the type quadratic, which we've gone over extensively. There's plenty of practice. Maybe I'll do some review on that one, but it'll probably be a mixed situation. But now let us creep over to non-quadratics. So again, this is a quadratic because it has exponent 2, exponent 1, and technically exponent 0. So when you have something of this form, where this is double of that one, and then this one is, and then the last exponent is 0, then it qualifies as falling under the quadratic form. Okay. But what if we have like something with exponent 3? All of a sudden, all our prior algorithms fail, which is why, I wouldn't recommend just simply memorizing algorithms straight up, unless you're really crunched in time for a test, and then you just want to learn how to mechanically solve the problems without too deep of an understanding. That's what I would discourage, but your time is your time. So with the quadratics, we have algorithms to factorize those, and then for general polynomials, we also have algorithms to try to solve for those. But unfortunately, they're a lot clunkier than the algorithms you've learned for solving quadratics, because quadratics are, by comparison, very simple compared to like a cubic. Alright, so if you have something like x cubed minus 1, well, you can't use x method here. Right? You can't use whatever methods you've learned at this point. But ultimately, the principle remains the same thing. And I'll show you in brief where the numbers are coming from yet again. So we're going to call this q of x. Our function is called q of x. And q of x consists of these three factors that I'm going to write out. So factor number 1 is x minus 1. And then factor number 2, let me change it all to plus. It'll be easier to follow the numbers. So the first factor will be x plus 1, and then the second factor will be x plus 2. And guess what the last one's going to be? X plus 3. I want to choose unique numbers so it's a lot clearer where things are going. So this one is the fully factored form, triple F, which is, again, these three are the factors of q of x. This is the answer that you want to get to, or this is the form that you want to get to. So this is not the problem. The problem is when I distribute this junk out. So let me distribute this first, following algorithm. It's just going to be square of the x. What is 2 plus 3? It is 5x. What is 2 times 3? It's just 6. And that is our familiar friend, the quadratic, but that's not our problem. This is the problem. This is a 2 by 3 distribution. Don't do foiling, because foiling is the 4-letter F word, and it only works for 2 by 2s, not 2 by 3s. So this one, just make sure you have good bookkeeping skills. So I'm going to mentally point to or visually point to this x, and then I'll distribute to this one first, which gives us x cubed. This one second, which gives us 5x squared. And then third, which gives us positive 6x. We are done distributing the x, so mentally you can, or even physically, you can use something to scratch it out so you don't have to deal with that nonsense anymore. Second distribution wave, we're going to do this one times that one, and I'm going to place it directly under here because they are both x squared types. I'm going to distribute this to that. We're going to get positive 5x, and then lastly this one, plus 6. So we have 6 terms, because if you distribute a 2 by 3, if you do this expansion, then 2 times 3 is 6. You should get 6 terms prior to simplification, in which case we do. So now we can just summate like terms, summate those, summate those. So x cubed plus 6x squared plus 11x plus 6. So that is the fully distributed q of x, and this is our actual problem, but I want you to pay attention to where the numbers are coming from yet again, and you will understand why you're doing the algorithm. And the algorithm kind of is awful, to be honest. So where is this 6 coming from? It comes from the product of just the constants. So constant number 1 times constant number 2 times constant number 3 is just distribution, because everything will be multiplied to everything else at some point. And that is where you get the 6. And as for this x cubed, well, similar to the quadratic, where this x squared comes from the product of x number 1 and x number 2, shouldn't it just be the product of the 3 x's? So x power 1, and then x power 1. If you multiply those, then you just get the x cubed. And you can imagine where these other numbers are coming from. But unfortunately, tracing the origins of these numbers is a lot more complicated than before, because now there's more of them and there's more things to keep track of. But this 6x squared came from all the products that had x squares in them, like this one. Where did that come from, right? It came from this one times that one. But where did this 5x come from? It came from this one times this one plus this one times this one. So there's a lot more back tracing to do. So we don't have a simple algorithm to figure it out like what you did for the quadratic, because when you work with quadratics, the steps of distribution is just a one-step distribution. So going back to this one, you have x plus 2 times x plus 3. And then when you're actually doing the problem, it just becomes a situation of asking, what are the factors of 6 that summate to make 5? It's just the 2 and the 3. So this is a single step process that leads to this situation. But unfortunately, getting to this 6x involved first getting that 5x from the quadratic distribution, and then you have to summate that to this other generation of exponent 2. So this one times this one is the other one you need to add up. So it's a lot more complicated where those numbers are coming from, but understand that they do come from somewhere. There is a physical mechanic that leads to, or not physical, there's an abstract concept that leads, there's a traceable, readable pathway that leads to 6x squared. It's just that the pathway is more convoluted than before, so we don't have a very simple algorithm to do it. But the only super clear origins stories are x cubed, the leading term here, and then the final term there. Because again, this one is simply the product of all those x's right there. And then this one is just the product of all the constants right there. So again, their origin stories are very clear. The origin stories of these two, a lot more complicated. So we're going to exploit, when we're doing these factoring of polynomials, we're going to exploit that this origin story is very simple, and then this origin story is very simple. So let's get to another example, because I think it'll make things a little more clear about what you're doing mechanically. So this is just q of x. Let's go to p of x, polynomial x. So polynomial of x consists of these factors right here. I'm gonna write them. I'm gonna put -2, and then I'm gonna put +1. This is just to illustrate a point, and then x plus -7. Well, let's do +7. All right. So these are the factors of p of x, and if again just following a quick algorithm, let me do these two first. So we're gonna get x squared. 1 plus 7 is 8. 8x, and then 1 times 7 gives us +7. We got to distribute that nonsense to x minus 2. Just follow good bookkeeping skills. First one to this. First one to the second. It's going to be 8x squared. First one to third. If we were finished, you could cross that out, and then this one times this one gives us, don't forget the signage, it's negative 2x squared. Notice the alignment. This one times this one gives us negative 16x. Lastly, negative times negative times positive is negative. 2 times 7 is 14. And all we need to do is summate. X cubed plus 6x squared. That's just a minus 9x, and then this one is nothing to it. It says minus 14, and that is the fully distributed version of p of x. So from here, full distribution to there. Again, make note of where things have come from. We have the x times x times x yields coefficient 1 invisible, 1x cubed. That's pretty straightforward. And then, of course, the multiplication of the constants, the -2 has to be multiplied to the 1, has to be multiplied to the 7, and then the product of those three numbers will get you the last one with a negative in the front, because one of these is a -2, and then the other two are positive. So that's where the numbers are coming from. You can trace where these 6x squared and then minus 9x are coming from, but again, it's hard to do it when you're going backwards. So if you consider distribution as going forwards, going backwards is a lot more complicated because more information has been lost or hidden along the way. So, two scenarios. Let's jump to a more complicated situation. So if we have, go back to f of x is equal to, I'm going to put a number 2x minus 1. So you can predict what that is going to do. And then we have x minus 3, and lastly, let's do 3x, and then plus 5. No, plus 2. Let's keep it simple. Plus 2. No, plus 5. I'll change my mind. Alright, so if we were to distribute this one, again, just follow typical conventions. Your favorite distribution algorithm. I'm going to distribute this first factor to the third factor. You can multiply in any order you wish, because we've committed a property. Alright, so this one times that one is unfortunately 6x squared. And then we have -3 plus 10x. -3x plus 10x gives us positive 7x. Lastly, -1 times positive 5 gives us -5. So again, I just multiply this factor times this factor, yielding this one. We still have this x minus 3 to distribute to this junk. So x minus 3, and again, or not again, but just to mention good form, make sure you slap on those parentheses. If you write it like this is technically wrong. If you plug this in your calculator, it will be wrong, because this one will be distributed to those three, but not the x. So, just a side note. So let's slap on those parentheticals. Again, good form. Have very good bookkeeping skills. So first distribution, second, thirdly. We are finished with the x distribution, and then now distribute the -3. I'm going to keep these in alignment order. That one gets us a -21x. And then lastly, negative times negative is positive. 3 times 5 is 15. Summate. Yikes. Minus 26x plus 15. So please pay attention to where these numbers are how these numbers are generated. In particular, only this one and this one. The rest of these, again, is too convoluted to trace. We have 2x times 1x times 3x, because 2 times 1 times 3 is 6x cubed. So this one makes sense where it's coming from. So again, this coefficient arose from the product of those three coefficients. And of course, we have this one right here. We have a... Ooh, I shouldn't block the numbers like that. Let me recircle. So this one times that one gets us this one. And then for the blue, we have the... Let's do purple. No, that's too... I don't like it. Let's do green. We have -1 times -3 is +3, and then +3 times 5 is 15, which is consistent with this last number right there. So those are the origin stories for those two terms, and that's understanding those ones is ultimately where we're going to be headed in terms of trying to factor out a generic polynomial. All right, so those are the things to emphasize. Let me write the problem. Let me generate a problem right on the spot. So E, F, G, H, I, J, K. Let's do K of X. I don't like I of X because I looks like an is by convention reserved for imaginary numbers. J, I don't like the little dot, but K is fairly simple. So K of X. This is the answer now, all right? So the answer is going to be x minus 1. I'm going to give myself very easy numbers, x plus 2. That is always the strategy. When you're doing the example, you give yourself the easy problems, and then when you make your students do the problems, you give them the hard numbers. Or you give them the decimal numbers just to make their life miserable. I'm just kidding. And then we have x minus 3. Maybe. Alright, so that is the answer. Well, let us do some quick distribution. You have minus 6, and then we have to distribute that. And if we distribute that, again, please have some sort of nice bookkeeping skills, unless you are a savant. In which case, you could probably just do this in your head, right? So you could do like 1,000 problems in 1,000 in like an absurd amount, an absurdly short amount of time. Lastly, we have this one plus 6, and hopefully I distribute things correctly, because if I had failed to distribute correctly, then the whole problem is bunk. All right, so it pays to double check. So positive, negative, negative. That's consistent, yes. And then we have negative, negative, positive, positive. Okay, seems consistent. I just want to double check. So minus 2x squared, summate, minus 5x plus 6. And again, this 6 arose from the product of those three numbers, and then this one arose as a product of those three variable numbers. But that's the answer, right? So let us start obliterating the pathway to getting to the problem. I should have undid. Okay, well, hopefully I remember to put a negative here, so I'm going to delete this part. Oh, goodness. Goodness gracious. And then minus. There you go. Alright, so this is the answer. I'm going to hide it behind my back like so. Well, let me shrink it first. Shrink. And then hide it. Take the problem, and I'll put it right here. So here we go. Here is a polynomial, and you are tasked with factorizing it. So again, this opening move is very similar to doing your quadratic. So you ask yourself, what are the factors of this 6 that will somehow intertwine with other factors, like right here, to come up with these ones? But you don't have to worry about the origin of those ones. So all we're doing is listing the factors of 6. So we have 1 and 6, but here is the deviation from prior methods. We're going to put them all like this. Well, you could use whatever visual organization you wish. It, quite frankly, doesn't matter. I'm going to do it like this. I'm going to put the 1, 2, 3, and 6 all together on top of a fraction bar, which we'll talk about why this fraction bar exists. And then, of course, we're going to have factors of 1. That's pretty straightforward. It's just 1. And then we'll have a plus or minus. Alright, so that's the main thing we're trying to do. So what exactly are we doing here? We're trying to come up with the origin story for this one, intertwined with this one, in order to generate one factoring candidate. We want to know what's a possible factor. So this is going to be factor number 1. We're just really curious, what is that going to be? And if you take that one factor we're trying to figure out using these numbers, and we multiply it to the rest of the function, then we should generate k of x. So that is the main idea of what we're doing. So again, when we're talking about these ones, we're trying to generate this particular factor. So if we multiply the factor, then we should get back to our original k of x function. So that's the idea. Again, kind of conceptually similar to working with quadratics, except again, it's harder to trace where things are going. So there's a bit more guess and check, unfortunately. Or rather, there's a lot more guess and check, depending on the severity of this degree. If this is degree 5, it's really, really annoying. Or if this is factor 60, you can imagine what a nightmare it is to come up with these ones. So if this had been like a 60 right here, and this had been like a 40, then that's a lot of number combinations. A lot of number candidates to try out, which is, honestly, no one's going to give you a problem like this. And if they do, well, just use the software, honestly. But this is what we have for this particular problem. So again, we're surmising that it's going to be something like x plus or minus some sort of number right there. And if you multiply to the rest, we're going to regenerate the k of x. So that's what's going to happen. So the question is, how do these numbers serve us if we can't do the backwards tracing as well as with quadratics? Well, we have to call upon division. All right. So first, understand what these candidates are. These are actually 0 candidates. Remember the introduction of this particular word? So if you take 6, for example, if this truly is the right candidate and you do minus 6, it will produce 0. If this is true, right? So if this is 6 and then this is truly a factor, then 6 minus 6 is 0, and then 0 times anything will give you 0. And that qualifies what it means to be a 0. So if it is correct. So the question is this the correct 0, right? So again, if it's the correct 0, 6, then the correct factor is x minus 6. Going back to what we talked about earlier, where if you have a 0, it is almost synonymous with factors. At least you can translate something as a 0 into a factor. So again, 6 translates into a factor of x minus 6 because that produces 0. So understand where this has come from. This has come from our candidate, this one. We're actually not sure if this is a factor. So how do we determine if this is a factor? There are multiple ways. You could actually, fun fact, you could just take the 6 and plug it directly in and crunch the numbers, and then if you get 0, it's a factor. But I'm not going to do that method because it gets aggravating cubing larger numbers like 6, 8, or 11, for example, or 2/3. It becomes needlessly annoying. So we're going to focus on this part right here. But I do need to cover something called long division, or in this situation, more specifically, synthetic division. So there's going to be a particular algorithm you're going to learn yet again. We just love algorithms. And basically, I'm just going to cover long division first. So this one, we're going to unfortunately put on hold, because in order to figure out if our candidate is good, we need this additional tool, and the additional tool is long division. So here's how we do this. We are hypothesizing that x minus 6 is going to be a factor. So if you hypothesize it's a factor, then if you divide the thing of interest, which is your function k of x, if you divide your function of interest by this factor, and this truly is a factor, then you should get a remainder of 0. This should feel kind of familiar, right? So this whole process is basically just this process, 2 into 1,256. Why did I choose these numbers? Because this is 1, technically negative 2, but just treat it as a 2, a 5, and a 6. So it's basically the same thing. So if you're trying to divide 1,256 by 2, and this is back in your days when you're like really following very basic algorithms, how many 2's fit into 1? None. How many 2's fit into the 12? Remember, once you can't fit any numbers, you have to move on to here, in which case it will now be 6. So you can fit 6 what? 6 2's into what? This whole 12. So 6 times 2 gives you 12, and that's what you are removing from here, because that's what it means to figure out how many fit inside. So how many 2's fit into 12? It's going to be 6 of them. As best as we can, so 12 minus 6 times 2 is 0. So that is a clean fit. And then we have dropping the 5 down right here, and then we ask ourselves the same question. How many whole 2's fit into this singular 5? The best we can do is 2. So what is 2 times 2? That's just 4, so we will have some leftovers. So from this 5, in which we're trying to fit in 2's, we can successfully fit 2 2's. So therefore, to fit means we're going to remove it. We have this leftover of 1. We carry down the 6. And we ask ourselves the last question, how many 2's fit into this 16? It's going to be a clean fit of 8, because 8 times 2 gives you 16. And if you remove 16 from 16, that gives you no more space, no more numbers in which we're trying to fit things. So remainder is 0. What this means for us is 2 is therefore a factor of 1,256. Why is that? Because numerically, after doing the division, we get a remainder of 0. And that's what it means to be a factor. If you divide a number candidate by the number you are considering, and you get remainder 0, then the number you are considering is a factor of the number in question. That's it. It's the exact same thing right here, except you now have x's instead of just having plain old numbers, but the process is exactly the same thing. So it's almost the exact same thing. It's a little more complicated though, but ultimately you're asking yourselves, how do I fit things into this other number thing? So here's the process for the long division for this polynomial considering this factor. So how many of the way it works is you don't really pay too much attention to this number when you're asking about fit. So going back to this numerical clean example, we ask ourselves how many 2's fit into this 1 first, right? And then when you can't fit any, then you move on to you drag the underline over to figure out, to ask yourself how many 2's can fit into this thing, into this 12. So one step at a time. So here's the process. You ask yourselves how many x's fit in terms of multiplication into x cubed. And the answer is only x squares. And that might feel kind of weird, right? Like typically we're used to actual clean discrete values like 6. There are 6 2's. There are 6 2's that fit into this 12. There are x squared of these x's that fit into this x cubed. So if you do x squared times x, then that's going to give you the perfect x cubed that you wish to subtract from here. Right? almost, because unfortunately this x here will get distributed to this x squared, but this negative 6 also has to get distributed to this x squared. So we have a little bit more work to do. X squared times negative 6 gives us negative 6x squared. And that is what we're subtracting, determining how many of those fit into here. So we do subtraction just like how we subtracted 4 from this 5. Because this 2 that's getting blocked off times this 2 only gives us 4. We have leftover, once we do 5 minus 4, we have leftover 1. So this one will also give us leftover analogous to that leftover. So perform the operations. This x squared, this x cubed cancels perfectly with this x cubed because we literally forced the fit. And then we have the second thing to contend with, negative 2x squared. Minus minus is positive. Okay, so negative 2 plus 6 gives us 4x squared. Why are we doing subtraction? Because that's the algorithm for this one. We're finding how many of these ones fit as best as possible into here. So when we're doing fitting, we're doing the removal just to see leftover space. So again, same ideas as in the old long division. Same idea. And like the old long division, we're going to drop this part that has yet to be done. So you bring down the negative 5x. I'm going to color it something else. Negative 5x, and then we move on to the next question. How many of this singular x power 1 fits into 4x squared? You ask yourself, this thing times what will duplicate this exact 4x squared? It's just going to be positive, because this is positive, positive 4x power 1. So what are we subtracting? What are we removing? We're removing the product of this one times here and times here. So let's do it. So 4x times singular x gives us 4x squared, because that's literally why we wrote this, because we're trying to remove the perfect number from here to determine fit. So those two will cancel out perfectly, but we have to do this distribution as well. 4 times negative 6 gives us negative 24x. Do the mathematics, but remember it's not minus plus this one. It's negative 5x minus negative, so it's plus 24. So 24 plus negative 5 gives us positive 19x. Alright, not quite done. We're going to take this negative 6, drop it down. Again, this is standard long division algorithm, like you take this 6 and you drop it down there. Same thing. How many, or what do we need to multiply here times this x to perfectly match this 19x? It's just going to be whole number 19. So we're going to have to subtract the product of this thing times those two. Because again, that's the whole point of long division. Figuring out how many of these fit into this remaining piece. Alright, so 19 times this one gives us exactly what we want, 19x. This is the unclean one typically. So 19 times negative 6 gives us a whopping... Hold up, let me do this. 6 times this is 120. We don't have 20 sixes, we only have 19 sixes, so minus 1 6 is 114. So 114. Cleanup step, the 19x cancels minus 19x perfectly. Which is, again, that's why we chose this 19, so that's going to be perfect. And then we have 6 minus minus, which is plus. So 6 plus 114 is 120. So, what's the interpretation? Unfortunately, this one is not a remainder of 0. It's a remainder 120. Not a remainder 0. That means what? Because we don't have a remainder of 0 like this one, that means this in particular is not a factor. So x minus 6 is not a factor of k of x. That's too bad. Just like how this one, well, not like just now, but to contrast with that, because we got a remainder of 0 when we're trying to divide by 2, that means that 2 is a factor. It is a factor of 1,256. All right. Wonderful. So what have we done? We figured out that that is not a factor. That's all we figured it out. So let me cheat just a little bit. Let's go over to... Let's go back to here. Again, we're trying to do long division in this situation. So let us try instead. Let's try to pick another candidate. This is still technically on hold, right? So let's pick 2. So maybe you're thinking, maybe 2 is a 0 of our function. So when you translate that into factor form, if you're hypothesizing 2 is a 0, then x minus 2 is going to be the factor. So x minus 2. We're hypothesizing, if we pick this one as a candidate, we're hypothesizing that this is a factor. So x minus 2 times some leftover junk should give us back to k of x. So again, how do we test to see if this candidate is a good candidate? We're going to have to do long division if you don't have synthetic division. So here we go. We're hypothesizing x minus 2 is a factor of that one. So let us crunch the numbers. So here we go. We ask ourselves, how many of those fit into this one? Or how can you perfectly match those two up? Well, it's going to be x squared. And you notice I put a little bit of spacing. This is just for bookkeeping skills. You can put it anywhere you wish, honestly, but I think I like to keep same degrees on top of same degrees. Alright, so this one times this one, because that's what we're removing. In order to see if it's a good fit, you have to take this, multiply to this, which yields this thing right here, and we're going to subtract it from here to determine the fit. The leftovers, I mean. So this one times this one. So this minus that, perfect cancellation. That's why we chose this. And then lastly, this one times this one. Minus minus is a plus. What do you know? So this one minus minus gives us 0. So these ones also perfectly cancel. Which sounds good, right? But no, we have leftovers right here, so we have to bring this down. So drop down the minus 5x. The question begins yet again. So what number needs to be here to multiply to this to perfectly match this one? Because we're determining fit. It has to be -5. You know, it's just copy. Exact same number. For this example. So -5 times x is what we shall remove. You know what? I'm sorry. Let me do one more thing. Should I do it now? No, I'm not going to do it now. Okay, never mind. Let's just keep going. So -5 times x gives us -5x. And then here's the funky part. It's going to be -5 times -2, which gives us +10. Yeah, I should have dropped it down. So the product of which is +10. There's no... We can perfectly subtract this -5x from that -5x. So that's perfect cancellation to produce 0. We have this awkward 10 that's being subtracted from nothing, which is why we should have dropped this 6. We should drop the 6 because there's only one term. We're trying to do 2 terms. So before, I should have just dropped the 6. Sorry. Now I'll drop it, because now this 10 can be subtracted from something, which is the 6 we've just dropped. Okay? So 6 minus 10 gives us -4. Is that a 0? Nope. It's remainder -4. And because it's not a remainder of 0, we can therefore conclude that x minus 2 is not a factor of k of x, because it failed to divide evenly, perfectly into this k of x right there. So again, if it's a factor, if something truly is a factor, after we execute division, we're supposed to get remainder 0. Since we did not get remainder 0, Therefore, this is not a factor. So you can begin to see the tedium of these types of problems. It's a lot of guessing and checking if you don't have a lot of training. If you haven't practiced these problems extensively, it's going to be a lot of clunky work. So let's pick the right 0. And I can pick the right 0 because I literally have the answer from before, if you recall. So in a way, it's kind of cheating, but this is just for illustrative purposes. So I'm going to delete we're going to delete this part right here because the candidate x minus 2 as a factor has failed. So that means that the 0 of 2 as a 0 has also failed. 2 is not a 0. Well, let me clean this up. Okay, again, so factors of 6, just to reintroduce the work, is 1, 2, 3, and 6. And then the factors of the 1 in front is just 1. We can have some sort of combo of pluses or minuses for our candidates. So when we see this 2, we already test tried 2 as a 0. It has failed. But technically, you can still use this 2. It could also be negative 2. It could be negative 2 as a 0. And from prior answer, that is correct. So let's see what happens when just by RNG you selected the correct candidate. So if our negative 2 as a 0 candidate is correct, then if you translate it into the factor becomes x plus 2. So understand how we can generate factors from zeros. It's literally what you need to add to produce 0. Positive 2. So x plus 2 is now our factor candidate. We're trying to divide k of x by our candidate. And if we produce a remainder of 0, then this is indeed a factor of k of x. So here comes the tedious work, copy paste. So there it is. This is exponent 3, exponent 2, exponent 1, exponent 0. So this is perfect fit into our division algorithm machine. We have to ask ourselves, what do we need to multiply to this x to perfectly match this? For removal, it has to be standard x squared. So this one times this one gives us x cubed, and then this times that one gives us positive 2x squared. Again, that seems perfect. Oh no, it is not perfect. So these two cancel out, produce 0, and then this one is negative, but minus positive gives you negative 4x squared. Okay, nothing unusual. We're going to drop this one down. Question begins anew. What do we need to multiply? What needs to be multiplied to this to get that? This has a coefficient of 1, which makes it very easy. It just needs to be negative 4. Negative 4 what? Negative 4x exponent 1. Because this times that will get you that. So minus, in parentheses, this one times this one. Again, it's always minus because you're seeing how things fit. Whatever leftovers you have to do subtraction. So this one times positive 2 gives us negative 8x. Close parentheticals and then execute the mathematics. So this is gone because that's what we did. That's why we picked those values. We have negative 5x minus. That's the double negative is plus. So negative 5 plus 8 gives us positive 3x. Lastly, drop down to 6. How can we get x to perfectly match 3x? That's just positive 3. So distribute to get to here. Subtracting what? 3x, 6, plus 6. Hey, what do you know? That's perfect. 3x minus 3x gives us 0, and then 6 minus positive 6 also gives us 0. What does this 0 mean? That 0 means that we have a remainder of 0. What does a remainder of 0 mean? It means that this thing here, therefore, is a factor of k of x. Wonderful, right? So now we could obliterate the rest of this nonsense. Perfect. What have we figured out? We figured out that x plus 2 is a factor of k of x. So if we factor out k of x plus 2 from k of x, that means we should get this thing, right? And that's just by virtue of how the long division works. So again, just to clarify, if you divide a simple number like 8, no, let's do 6. If you take a number like 6, and then you do long division, in this case it's very short, but if you divide by 2, then you're going to get 3, right? So there are multiple conclusions there are multiple things we can say when we have something like this. We can say 2 is a factor of 6 because we get a remainder of 0, right? We can say 3 is also a factor of 6 because 3 times 2 gets you back to 6. And we already know 2 is a factor of 6 because the long division produced remainder 0. Okay, so let's rewrite this. That means that 2 times red 3 gives us the original 6. And by analogy, it's this blue thing, like this 2, times this upper thing, which is red, just like this 3 thing. If you do blue times red, then you're supposed to get purple, magenta, which is this thing on the inside. That one. So, exact same analogy, alright? It's the exact same situation. Let's obliterate that. But here's the thing, though. This is a factor. Yes, this is technically a factor of k of x, but it is not fully factored. But this is our old friend, the quadratic. What factors of 3 that have the same signs summate to be -4? So, without doing too much work, I'm just going to run through it. There it is. So we have factor number 1, we have factor number 2, and then we have factor number 3. When you multiply those 3 things, you will regenerate the k of x in fully distributed form. So this is just k of x in fully factored form. So let's write that down. And there you go. Factor number 1, factor number 2, factor number 3. We got these ones by factorizing the quadratic because it's very simple. We got the x plus 2 by doing multiple test candidates, by doing long division. That's how we generated this factor. So far we only have long division at our disposal. I'm actually going to end it here. It's going to be a very short time today because I need to go on a walk with my roomie. We're going to walk because exercise is good. You got to get the blood flowing. Better not sit around too long because humans are not supposed to be sedentary for hours at a time. It is bad for our health. So I'm going to go for a walk. I'm going to resume activities later. So very short session today, but again, I'm going to cover the other cases afterwards. Alright, until then, have a good one. Hopefully, we'll see you in the next.